this union of lines, all in different directions. Okay, now in dimension 2, this has been known for a while. In dimension 3, this was spectacularly solved by Hong Wang and Joshua Zoll. And roughly what they did is they first proved a very special case of the Kekaic conjecture, which we'll call the sticky version of the Kekaic conjecture. So roughly speaking, stickiness means that your set of lines has a self-similar structure. So this is like, has a fractal structure. And this special case makes the problem easier. So this was already a big breakthrough. Then just last year, well, this is a special case, so you of course get this arrow, but just last year, they proved that this direction is true, and n equals 3. This was big math news. I would encourage you to look at Quanta for some of the nice videos about this. Okay, great. So we have this special case. We have a lot of really nice progress on this special case. Slowly, researchers are figuring out how to move up the ladder and get up to the restriction conjecture, and even beyond. This is still very open. Now over on this side, we have a much more general version of this picture. So we replaced the restriction conjecture with a much more general question about wave interference, which is called the Hormander dichotomy conjecture. Okay, so very general. And restriction is a special case. Now, we get the same types of implications. So the Hormander dichotomy conjecture implies a curved version of the Kekaic conjecture. So let's think about instead a union of curves. And in the same way that you can set up stickiness for Kekaic sets of lines, you can set up stickiness for Kekaic sets of curves. Okay. Now, in my work, I proved, this came as a surprise to me, that once you know the sticky version of the Kekaic set conjecture for lines, you know it automatically for curves. So this is my work. But I also found some examples which show that this direction, it's going to require a lot of new ideas. So I'm thinking about this one. Okay, and the eventual goal is to move all the way up to here and get a robust characterization of some oscillatory integral operators.